In 1998, a photon decided how to behave after it had already been detected. The entire foundation of causality was suddenly up for grabs. The strangest part: the physicists who proved this were just as stunned as everyone else. This was the delayed choice quantum erasure, a variation of Thomas Young's classic double-slit experiment from 1801. For 2 centuries, Young's simple experiment had been the gateway to understanding light's dual nature. A beam passing through 2 narrow slits produced an interference pattern on a screen. The photon behaved like a particle. Light, it seemed, changed its nature based on whether someone was watching. This was the crisis Niels Bohr formalized in 1927 with his principle of complementarity. You can observe one or the other, but never both simultaneously. It was a neat, if unsettling, rule until Marlan, Scully, and Drühl decided to push it to its breaking point. In 1982, they published a paper titled Quantum Erasure, a proposed photon correlation experiment concerning observation and delayed choice in quantum mechanics. Wheeler had imagined a cosmic version. A quasar billions of light-years away sends photons toward Earth. If an astronomer decides after the photon arrives which path to measure, does that decision retroactively determine the photon's journey? They proposed entangling each photon with a second particle that carried which path information, as long as that information existed. But here was the twist. If they erased that information after the photon had already been detected, the choice to erase or preserve the data happened after the photon had already hit the screen. Yet the photons passed. Raymond Chow, Paul Kwiat, and A. Steinberg carried out the experiment. It worked exactly as Scully and Drühl predicted. The interference pattern re-emerged. The universe, it seemed, did not care about your timeline. But to understand why a single photon can dismantle our most basic assumptions about reality, we have to go back to the beginning, back to a lecture hall in London. He was about to perform a deceptively simple experiment. He cut 2 narrow slits in a screen. What he saw was not 2 bright stripes, as one might expect from particles passing through 2 openings. This was an interference pattern, the unmistakable signature of a wave. Light, Young argued. For a century, this settled the matter. End of story. Then came the quantum revolution. In the early 20th century, physicists discovered that light also arrives in discrete packets of energy. A wave or a particle. The double-slit experiment was resurrected. Scientists fired single photons, one at a time, toward the 2 slits. If light were a particle, over time you would expect 2 piles of hits, one behind each slit. When the photons were fired one by one, with no detector watching, each individual photon seemed to interfere with itself. Each photon, it appeared, traveled both paths simultaneously. It existed in a superposition of states. This is where the crisis deepens. Place a detector at one of the slits to determine which path the photon actually took. Suddenly, each photon behaves like a classical particle, choosing one slit and landing accordingly. The act of measurement. This is not because the detector physically disturbs the photon, even the most delicate. The universe seems to enforce a rule. You can know the path, or you can see the interference, but never both. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper at the Institute for Advanced Study in Princeton that aimed to expose a fatal flaw in quantum mechanics. It described a scenario where two particles become entangled, their properties linked across any distance. Einstein called this spooky action at a distance. He believed there must be hidden variables, local properties we simply could not see. But the universe, it turned out, does play dice, and it refuses to let anyone peek at the loaded numbers. Bohr's response to Einstein was the principle of complementarity, formalized at the 1927 Solvay conference in Brussels. They are complementary. You can never observe both simultaneously because the experimental setup that reveals one necessarily obscures the other. It is not a limitation of our technology. It is a fundamental feature of reality. The photon does not possess a definite path until it is measured. The measurement does not reveal a pre-existing reality, then Keynes creates one. This was the philosophical earthquake. Observation, in the Copenhagen Interpretation, it defines it. There is no deep objective reality beneath the measurements. There is only the quantum state, and the act of looking forces it to choose a face. The paper Scully and Drühl published in 1982 did not just propose another experiment. It identified a loophole in Bohr's complementarity, a crack in the wall between wave and particle that no one had previously exploited. You placed a detector at the slit, and that detector interacted with the photon, scattering it, absorbing it, or altering its momentum. Bohr's defenders could always argue that the disturbance itself destroyed the interference. The photon did not change its behavior because of some metaphysical choice. Scully and Drühl realized they could mark the photon without touching it. Instead of measuring the photon directly, they would entangle it with a second particle, another photon, or an atom, that would carry the witch path information. Its entangled partner would sit in a separate apparatus, silently holding the knowledge of which slit the first photon had passed through. And yet, the interference pattern would vanish. The mere existence of that information elsewhere in the universe, the photon behaved as a particle, not because it was disturbed, but because the universe kept a record. Eugene Wigner's deep focus on the measurement problem, the question of what constitutes an observation, provided the philosophical foundation. Conversations with Nobel laureate Willis Lamb, who had questioned whether the act of measurement was as absolute as Bohr claimed, gave Scully and Drühl the confidence to challenge orthodoxy. Wheeler had imagined a photon from a distant quasar, split by a gravitational lens, arriving at Earth billions of years later. If the choice came after the fact, what did that say about causality? In Scully and Drühl's setup, a laser fires a pulse of light through a nonlinear crystal, producing pairs of entangled photons. The other photon goes to a separate detector, a quantum marker that records which slit the first photon passed through. The first photon reaches the screen. A dot appears. And then, after that dot has already been recorded, if the marker is red, the witch path information is preserved, and the photon's landing pattern shows no interference. The photon's past, its behavior at the moment it passed through the slits, appears to change based on a decision made after it had already arrived. Wheeler's delayed choice thought experiment had proposed exactly this. Scully and Drühl proved it was experimentally feasible. They showed that the decision to erase or preserve the information could be delayed until after the photon had been detected. The photon did not know. At the moment it passed through the slits, whether its path would later be erased, it could not know. The information had not yet been destroyed, and yet, when the experiment was run, the universe seemed to allow the future to define the past. The photon's behavior at the slits was not determined until the experimenter decided. This was not retrocausality in the sense of rewriting history. The dots were already there. But when the experimenter sorted the data, grouping the photons whose which path information had been erased, one subset showed interference. The same photon, the same screen, the same moment. The photon's past, in terms of what it meant, was not fixed until that decision was made. The University of Rochester team, Raymond Chow, Paul Kwiat, and A. Steinberg Slessen, took Scully and Drühl's theoretical blueprint and built it into a working apparatus. By 1998, they had demonstrated the quantum eraser in a real laboratory. Their setup used a nonlinear crystal to generate pairs of entangled photons. One photon traveled through a beam splitter, effectively creating two possible paths. At the far end, 4 detectors, labeled D1, D2, D3, and D4, captured the results. When the experimenters preserved the which path information by reading the entangled partner, when they erased that information, the interference pattern re-emerged. The photon's behavior at the beam splitter, whether it acted as a particle or a wave. But the most unsettling detail was the space-like separation. The decision to erase or preserve the which path information happened at a location far enough from the photon's detection point. The choice and the erasure were separated by a distance greater than light could cross during the interval between the photon's arrival and the experimenter's decision. The universe was not sending a signal backward in time. It was simply refusing to assign a definite pass to the photon. The photon did not have a history until the experimenter decided what to do with the data. In 2002, a team at the Universidade Federal de Minas Gerais in Brazil, P. Walborn, O. Terra Cunha, Padua, and C.H. Monken published a new version of the experiment in Physical Review A. They used an actual double slit. Instead of beam splitters, they employed polarizing optics to mark which slit each photon had passed through. Again, the results were unambiguous. When the which path information was erased after detection, the interference pattern reappeared. The experiment reinforced the same conclusion. The photon's behavior was not fixed at the moment it passed through the slits. In 2023, a paper published in Scientific Reports, part of the Nature portfolio, pushed the experiment even further. Researchers used coherent photons from an attenuated continuous wave laser, stable controlled source, that eliminated many of the experimental uncertainties from earlier setups. They employed a Mach-Zehnder interferometer composed of a polarizing beam splitter and a standard beam splitter, configured to enforce particle-like behavior according to the Fresnel-Arago laws. The which path information was completely erased by a polarizer choice made after space-like separation. The predetermined which-way information of the photons was erased by a decision made after the photons had already been detected. This is not time travel. No one is sending messages backward. The photon does not physically change its trajectory after the fact. What changes is the interpretation of the data. But that distinction is subtle, and it hides a deeper truth. The universe does not store a complete record of every particle's history. It does not keep a ledger. The past is not a fixed, immutable sequence of events. It is a set of possibilities that only crystallizes when information is either preserved or destroyed. The universe does not remember either. The only thing that exists is the quantum state, and the quantum state is a cloud of potential until something. Here is the real problem with how this experiment is often portrayed in popular science. The truth is stranger and more subtle. The delayed choice quantum erasure does not involve retrocausality. No information travels backward in time. What is actually happening is far more unsettling. Reality is contextual, and the context is defined by the experimenter's choice of what to measure. The quantum eraser has no effect on the original screen at D1. The full data set, the pattern is a random scatter of dots. Only when the experimenter goes back and sorts the photons into two groups. One subset shows interference. The interference pattern is not physically present on the screen. It exists only in the coincidence counting, Zortum betas, in the correlation between the photon's arrival and the later decision to erase or preserve its which path information. This is not magic. It is the logical consequence of entanglement and post-selection. When the experimenter decides to erase the which path information, they are not changing the photon's past. That subset, when isolated, exhibits wave-like behavior. The complementary subset, the full dataset, containing both subsets, shows no pattern at all. It simply refuses to assign a definite history until the information is either retained or destroyed. It is fixed only when the experimenter decides what to do with the information. Complementarity, as Bohr formulated it, is not a limitation of measurement. They cannot coexist. Even when the which path information is stored in an entangled particle, the mere existence of that information anywhere in the universe is enough to collapse the wave function. It does not need to be observed, it only needs to be correlated with a record. The universe keeps a ledger, and the ledger defines reality. Properties of quantum systems do not exist until they are measured. It exists in a superposition of possibilities, a cloud of potential, until a measurement forces it to become something specific. It creates one. The experimenter's choice of what to measure, whether to preserve or erase the which path information. The photon's behavior is not independent of the observer. This is the lie that the single photon exposes. The reality we experience in world of definite objects. It is an approximation, a coarse-grained projection of a deeper, stranger substrate. There are only relationships. There are only correlations. The photon does not travel through one slit or the other. It travels through both, or neither, or something in between, depending entirely on what information is later retained or erased. The unanswered question, the one that keeps physicists awake at 3 a.m., is this: if quantum mechanics is correct, and every experiment to date confirms it is, then what does this say about time, causality, and the nature of reality itself? The future does not cause the past, but the future does define the context in which the past becomes meaningful. The universe is not a clockwork mechanism, winding forward from a fixed beginning. It is a web of correlations where the meaning of any event is determined by the choices made later in the chain. The delayed choice quantum eraser does not prove that reality is a lie. It proves that reality is contextual. It is not fixed. It is not independent. It is defined by the questions we ask and the choices we make. The photon does not know its own history until we decide what to remember and what to forget. And in that sense, the experiment is not about photons at all. It is about the nature of knowledge, the limits of observation, and the strange, beautiful truth that the universe is not only stranger than we suppose,